And today we'll be discussing BJTs because that's the only remaining topic that we had throughout the semester. And during the hurricane, we missed a couple of lectures. And this is what we planned to cover at that time. Now, if you think about it, at that time, we did not have a very good idea about MOSFETs or how transistors work. So the way I would have planned to cover BJTs would be very different if I had taught it at that time. So now, since you already have a good idea about MOSFETs, what I'll try to do, I'll try to relate the concepts of BJT with whatever you have already learned related to MOSFETs. So just think about how MOSFETs work and try to sort of correlate with whatever you'll be learning on BJTs in these two lectures. Okay, so I'll always try to compare them with MOSFETs and try to show the analogy that how they are same, how they are similar, and how they are different in certain cases. Okay. And to learn about BJTs, the first thing that you need to sort of revisit is the diodes, because BJT is nothing but two back-to-back diodes connected together, right? So when you think about diodes, remember that we had looked into the details of how a diode is sort of designed. So it's a PN junction diode, right? So you always have a P-type semiconductor and an N-type semiconductor, and you sort of try to fuse them together. There are two different modes of operation, either forward bias or reverse bias. So please go back to those topics or those discussions that we had earlier in the semester. But what we wanted to sort of point out from there is that the way the diode behaves is sort of like a one-way switch or a one-way gate. It lets the current flow in only one direction. It does not let the current flow in the other direction. So that's the property, or that's the ideal behavior of the diode, that you would want the current to flow in only one direction. If you have the current flowing in the other direction, it will not happen through a diode. So that's where the concepts of forward bias and reverse bias comes in. And if you draw the ID versus VD characteristic of a diode, that would ideally look like this. VD is the voltage drop across the diode, and ID is the current through the diode. So as you see that ideally, when VD is negative, the diode is off, it is reverse bias. And again, ideally speaking, if as soon as the diode becomes forward bias, you should see a large increase in the current. But that is again the ideal behavior of a switch, or ideal behavior how the diode should turn on. Practically, you'll see that after a threshold voltage, the diode will turn on and the ID versus VD characteristic will look like this, right? So that's the forward bias diode's characteristic. Sometimes you even simplify that and you say that my ID versus VD characteristic looks like this, that at a particular threshold voltage, V threshold, I'll suddenly see a sharp increase in the current. And I'll show you how that assumption is sort of justified, that after a certain threshold voltage, you can expect your current to increase many folds within a very short VDS. So even if the diode voltage does not change by a large amount, the current can change by a large amount once it has crossed the threshold. And that comes from the equation that we have already derived this equation and showed how it comes, or discussed what's the implication of this equation. So ID is the diode current. That is basically IS. That's the saturation current, or sometimes referred to as the dark current of the diode. This is basically the reverse saturation current. Now that multiplied with e to the power VD over VT, that gives you the forward bias diode current. Remember, VD is the forward bias, the voltage that you're applying across the diode, and VT is something that is called a thermal voltage. So this is not the threshold voltage. So this VT is the thermal voltage of the diode, which is KT over Q. And the value of the thermal voltage is about 25 millivolts. This is again just recapitulating what we have learned when we studied diodes. So now IS is the saturation current, and typically the value of IS is in the range of 10 to the power minus 15 ampere. So 1 femtoampere to, let's say, 10 to the power minus 17 ampere. So that's a very small amount of current that you expect from the diode. And you can write the expression for VD as VT times natural logarithm of ID over IS. So that comes from equation. So if I mark this as equation 1, equation 2 just comes from equation 1, that you are trying to find out VD as VT multiplied with natural logarithm of ID over IS. Now, you know that the current that is flowing through the diode, for all practical purposes, it's a few tens of microampere to hundreds of microampere to even a milliampere, right? And IS is something that we noted as 10 to the power minus 15 ampere. So this ratio is almost 10 to the power 12. So this is a large ratio. That's something you need to keep in mind. And for practical values of, let's say VT and the ratio of ID over IS, VD, that's the diode voltage, and that's the drop across the diode, that is in the range of 0.5 to 0.8 volts. So if we just take a few examples, I think those examples are somewhere over here. So let's say my VT is 0.25, that's the 25 millivolt. And let's say the natural logarithm that I'm looking at, this is the natural logarithm of ID over IS. So that's the diode current over the saturation current. So if this is 10 to the power 10, so the value of your VD will be 0.58 volts or 580 millivolts. If it is 10 to the power 13, you see that it's only 0.78 volt or 780 millivolts. So the diode voltage, the voltage across the diode did not change much, even though the current across the diode changed by 1,000 times, right? So in this case, the ratio of ID over IS was 10 power 10. In the second case, the ratio of ID over IS is 10 power 13. So the ratio of the current or the ratio of ID over IS changed by 1,000 times, but your VD, the voltage drop across the diode, changed by only 200 millivolts, right? And this is something that you can readily prove that whenever your ratio of current changes by 10 times, the natural logarithm of 10 is 2.3 or 2.303, something like that, right? So that multiplied with 25 millivolts, that gives you a change in VD of only 75 millivolts. So as the current changes by, let's say 10 times, your voltage across the diode will only change by 75 millivolts, right? That's why people sometimes approximate it as a certain value. Even though the current across current through the diode is changing by 1,000 times, the voltage across the diode, that is fixed around, let's say someone can approximate this as 0.6, someone can approximate as 0.65 or 0.7. Everything is sort of similar, right? So for example, in most of the books that you'll see that it is approximated as 0.7 volts because it's not changing in a large range, even though the current is changing in a large range of operation, right? So that's the, and this is the same equation that we had been talking about for the past few minutes, that your drop across the diode is VT or the thermal voltage times ln of ID over IS. Even though the ratio of currents change by a large amount, the voltage will not change by a large amount. So that's why it's okay to approximate this voltage to be a constant voltage. So even though the current changes by something like this, an exponential term, sometimes people just approximate the voltage across the diode by a constant quantity, which is the threshold voltage of the diode, and assume that the current increases exponentially at that point, or current increases by a large amount at that point, right? So that's an assumption which is okay for simplistic calculations. So usually you'll see in books that you'll always see this VD or the voltage drop across diode is assumed to be 0.7 volts. But you need to keep in mind that that's not true. It can vary depending on the amount of current that is flowing through the diode, but it is okay to approximate it to be a certain value around 0.7 volts, as we have found from the numbers. Now, what is a BJT? What is a bipolar junction transistor? The bipolar junction transistor is just sort of two diodes fused together. So we have learned about PN junction diode, right? So when you, instead of PN, when you have PNP, that is, you have a P-type semiconductor followed by an N-type semiconductor followed by a P-type semiconductor, you form a BJT. Similarly, if you have NPN, you again form a BJT, right? So BJT is just two diodes sort of fused together back to back. But there are more things to it. It's not as easy. You cannot just take two diodes and connect them back to back. It will not form a BJT. So there is a design concern. The three regions in a BJT are called emitter, base, and collector. Just like in a MOSFET, they are called source, gate, and drain. For BJTs, they will be called emitter, base, and collector. And the way the BJT behaves or operates is also a little bit different. But they are also similar in a way that in terms of MOSFETs, you know what is the job of the source. It's the source for the carriers, for the majority carriers, right? So for an N-channel MOSFET, the source is the source of electrons. For a P-channel MOSFET, the source is a source of holes. Similarly, the job of emitter is exactly the same. It will emit the majority carriers. So if you're talking about an NPN transistor, that emits, so the emitter is N-type, the base is P-type, the collector is N-type. So the emitter will emit N-type carriers or electrons. Again, for PNP, emitter, base, collector. So the emitter is P-type, which means that it will emit P-type carriers or holes. Okay, so in that way, they're pretty much similar to how a structure of MOSFET and that you already know of. But one important difference here is that, and which is the most important difference, is that the MOSFET is a voltage controlled current source. The MOSFET is a transconductance amplifier in its very basic terms, that you apply a voltage at its gate, you get a current at its drain, right? So your voltage at the input gets converted to the current at the output. In case of a BJT, you will apply a current at the input, you'll apply a current at the base, you'll get back a current at the collector or at the emitter. So it's a current controlled current source instead of a voltage controlled current source. And that's the main difference between a BJT and a MOSFET. The MOSFET is a voltage controlled current source. The BJT is a current controlled current source. Now, there is another consideration there, that how does the current flow in a BJT? So, for example, if you look at the structure of a BJT, so for example, here you have an N-type layer, which is your collector. You have a P-type layer in between, which is your base, and then again you have a N-type layer, which is your emitter. So this is your emitter, this is your base, and again this is your collector. So those are the N, P, and N-type semiconductors that you have in the structure. So one very important consideration is that your base needs to be extremely small. So whatever is in the middle, be it a PNP, in that case, this is the N-type semiconductor that we are talking about, or when you're talking about NPN, the P-type semiconductor needs to be, the region needs to be extremely small. The base region needs to be extremely small. And why is that? The primary reason behind that is basically when we are talking about MOSFETs. Remember that we said that during saturation, what happens is that from the source, you see that there is an influx of the carriers, right? The source will create a lot of carriers, and that will pass through the channel, and that will be available at the drain, right? So remember that in case of saturation in MOSFETs, the channel is pinched off, right? So the channel does not exist fully between the source and the drain. So what did we say, that how does the electrons or holes, the carriers, traverse from the source to the drain? It's mostly because of the effect of the field, or in other words, because of the field, the carriers have a certain velocity, and because of that velocity, because of that inertia, once they have started their travel from the source side, they will reach to the drain side anyway. Remember that the energy band diagrams that we had drawn, that you're on top of the mountain already. So if you start rolling, if the ball starts rolling from the top of the mountain, it will eventually come down at the bottom of the mountain, right? So that was the analogy that we gave in terms of mechanical inertia. So in this case, it's not a mechanical inertia, but it's an analogy that you already have an electric field, and your carriers have already been subjected to that electric field. They will eventually reach from the source to the drain, even though the channel was not continuous. So that was true for MOSFETs. For BJTs also, the carriers are moving from, let's say, the emitter side to the collector side, right? Emitter is the source. It will emit the carriers, right? And collector is the collector of carriers. So you have your carriers, the traversal of the carriers have already started, right? So the carriers are already moving. They have been emitted from the emitter. They're moving towards the collector. Unless the base is very small, you might lose this inertia, right? Let's say my base is a kilometer long. Would the electrons, can the electrons or holes traverse from the source and drain? Or in this case, between the emitter and the collector? If my base is extremely long, let's say a kilometer long semiconductor, it cannot, right? So it will not have enough inertia. Again, inertia is an analogy here, but you can think of it in that terms. So the base has to be very small for the carriers to start from the emitter, cross the base region, and be available at the collector. Okay. So, and remember that you don't have a channel in this case. It's always NPN. In case of MOSFETs, you had the N channel or N-type source. then you created an N-type channel, and then you had an N-type drain, right? So there was a continuous N-type semiconductor in case of the MOSFET. Here you don't have the continuous N-type semiconductor, so you're more reliant on the drift of the carriers here, right? So in terms of, so when you study a semiconductor physics class, you will know these differences between the drift current and the diffusion current. So when the device is on, it mostly happens through the drift current, which I am giving as an analogy of this inertia, right? So this drift is basically analogous to the inertia that I am talking about. Now, the takeaway is that the base region has to be extremely small. If it is a large base, it cannot work as a BJT. You cannot really get the drift currents to flow from one side to the other, right? Or in other words, there will be no flow of carriers from the emitter side to the collector side. So it's of paramount importance that your base region be extremely small, right? So that's why if you just connect two diodes together, it will most likely not work as a BJT because your base region will be too big. Okay, so now this is the overall structure of the BJT. You have the N-type collector, you will have the P-type base, and you will have the N-type emitter. So this is an NPN BJT, right? And we'll again discuss mostly NPN, which is analogous to an N-channel MOSFET. And the PNP will, of course, be the dual of that, just like a P-channel MOSFET or a PMOS. So if you look at the top view, you'll be seeing these connectors coming out of the BJT. So you'll have a collector, you will have a base, you'll have the emitter, and this is the substrate connection to the BJT. Okay, and remember that in most of the semiconductor wafers, the substrate is a P-type, and on that P-type substrate, you create different P layers or N layers to create your overall structure. The same thing that you do for MOSFET, you'll have to do a similar thing for BJTs, that you'll start with only this P-channel substrate or P-type substrate, and then you create an N-type layer, which will be your collector. Inside that N-type layer, you'll create a P-type layer, which will be your base, and inside your base, you'll create another N-type layer, which will become your emitter eventually. The symbol for this NPN BJT is something like this. So as you see that it is again very similar to your N-channel MOSFET, right? So this was my N-channel MOSFET, right? This was my drain, this was my source, this was my gate. When we are talking about NPN BJTs, the symbol is sort of like this. And in case of source, you'll have emitter. In the place of drain, you'll have collector. And in the place of gate, you'll have a base. Okay. So in that way, they are also again very much analogous and very much similar to each other. This just shows a simple planar NPN transistor, something that we had already drawn before, that you have this NPN structured inside of this N structure, inside a P structure. So that creates your emitter and base. And then you have your collector and everything is built on top of a P substrate. Now remember that this diagram or this drawing is not to scale. So that's why you have a large base region here. But in an actual BJT, as I said, that the base region has to be very small. So it would probably look more like this, that this entire region will be your emitter. You'll have a very small base, and then you'll have a large collector again. So this is not drawn to scale. So that's something you need to keep in mind. Okay, so how to sort of analyze these BJTs, or what is the main difference in terms of the equations that we write? So you see that this is again, this circuit diagram is again very similar to what you have learned for an NMOS transistor, right? So instead of an NMOS transistor, we have an NPN BJT here. Now remember, for MOSFETs, it's metal oxide semiconductor, right? So there is an oxide layer between the metal and the semiconductor, which does not let any current flow through the gate. So there is no current through the gate for a MOSFET. For a BJT, it's an NPN, NP, and N semiconductor, right? So if you are sending a current through the base, there is a forward bias happening if you have a positive VBE here. So because remember, this is N, the base is P, and the emitter is again N. So if you are applying a positive V base to emitter, so the base to emitter voltage is positive, which means you have a positive potential at P and a negative potential at N. That means that you have a forward bias happening at the base emitter junction of this BJT, right? So you have a forward bias diode. What is the equation for a forward bias diode? Again, we are writing the same equation, ID equal to IS times e to the power VD over VT. What is your VD? That's the diode voltage. What is the diode voltage in this case? The base to emitter voltage, because my diode is in between my base and emitter. So the base to emitter voltage is my entire diode voltage, right? The diode is in between your base and your emitter. So VBE is your VD. That's the diode voltage. And KT over Q is your thermal voltage again, right? Of course, if you really want to be exact, you can write down the exact equation, which is this -1. But for all practical purposes, again, we can ignore that, right? So when we studied diode, we studied this equation as IS times e to the power VD over VT -1. But keep in mind that in this case, we are just ignoring it because it doesn't make much of a difference. It's just, if you think about the VD, it's just 25 millivolt difference. Okay. All right. So again, your VBE, that is VT times ln of ID over IS, that is almost equal to 0.7 volt. That's a forward bias diodes drop. So the VBE for an on BJT, whenever the BJT is on, your VBE will be about 0.7 volts. And that's something you can always assume while solving a circuit. It may not be 0.7 volts, it could be 0.65 volts, but that does not make a huge difference in your analysis. Okay. And again, this is something we had shown before, that the thermal voltage multiplied with ln of 10 power 10 is 580 millivolts, ln of 10 power 13 is 780 millivolts. So it's not a huge difference or a huge error in terms of assuming VBE as 0.7 volts, right? So that's why people always assume that the VBE drop for a BJT, that's the base to emitter drop for a BJT, is always 0.7 volts. That's usually assumed to be a constant. All right. Now, if you think about the, so we know about the ID VDS characteristic of the MOSFET. That is the output characteristic of the MOSFET. ID is my output current, VDS is my output voltage. Similarly, for BJTs, you have IC versus VCE. IC is your output current. So collector is analogous to your drain, right? And CE, that's the collector to emitter, is analogous to your drain to source, right? So IC versus VCE, that will be exactly analogous to your ID versus VDS characteristic that you have learned for MOSFETs. All right. So as you see that this is also very similar. And one important aspect here is that usually if you look into books, that this saturation region, we call this saturation region for MOSFET. And there is a very good reason to call it the saturation region, right? Why? Because your current was saturated. You see that the current is saturated. It's a constant quantity as you are changing the x-axis. So in case of MOSFETs, we call this the saturation region. Sometime in the notes you saw that it was also termed as the active region. So saturation or active meant the same thing. Interestingly, for BJTs, this is called a forward active region, but we never call it a saturation region. So, and there's a historical reason behind that. So for BJTs, the saturation is this part of the curve, and this can make you confused. Like, this is a very confusing thing. For MOSFETs, this part was called the linear region or the triode region. For BJTs, this will be called the saturation region, whereas this is only called the active region. Right? Now, why this is called the saturation region for BJTs? There's again, as I have been saying, that it's a historical reason that people started with vacuum tube triodes when people tried different configurations of these semiconductor devices. From vacuum tube triodes, there came the theory of JFETs and MOSFETs. And then William Shockley and John Bardeen and Walter Brattain, they developed BJTs, I think around 1947 or 1948. MOSFETs were not built up till that point. So now, when you think about what's happening in this region, this is the region where your transistor is on, your BJT is on, So your emitter is emitting a lot of carriers. Okay. Now, if your collector voltage or VCE is not high enough, those emitted carriers cannot travel to the collector. So remember the structure of the BJT. So I am emitting my carriers. So in this case, it's done. So this is the emitter, right? For NPN type BJT. And this is the direction of the current, which means the emission of the carriers is happening on the other direction. It's an NPN BJT. So the majority carriers are the electrons. So electron flow is in the other direction of the arrow. So electrons are flowing inside the base and then towards the collector. Now, if your collector voltage is not positive enough, it cannot collect or it cannot attract the electrons that have already reached the base, right? So remember that for NPN, you need to have a positive VBE. Your VBE needs to be positive for the transistor to turn on, and you need to have a positive VCE. Why? Because the emitter is emitting your electrons. They are going towards your base, and then they are supposed to go to the collector and be collected, right? But if the collector voltage is not high enough, all the emitters or all the carriers that have been emitted and that have been accumulating at the base, those carriers cannot be collected at the collector side if the collector voltage is small. You're not providing enough positive voltage for the electrons to pass from base to collector. That's what is happening in this region. So what is actually happening is that inside the base, you're getting a saturation of carriers. So your base is getting saturated with carriers. There are so many carriers inside the base. And by carriers, I mean the majority carriers in the emitter or the majority carriers in the collector side. There are so many carriers inside the base that the base is getting saturated and the collector is not collecting enough of them. That's what is happening in this region. And the way the transistors or the BJTs were first described, this is the way it had been described, that, okay, we have a saturation of carriers in the base region when your VC is low, and that's why you are calling it a saturation region, right? So it's a different kind of saturation. It's not that the current is getting saturated. The current is getting saturated here. So it is very easy to understand in case of MOSFETs. In case of MOSFET, this is called the saturation region or the active region because your current is saturated. In case of BJTs, this is called the saturation region because in this region, you have a saturation of carriers inside the base. So the way they were described, different people worked on BJTs and MOSFETs 70 years ago, right? So the same people who are working on BJTs, they are not working in MOSFETs or vice versa. So the way they had been described, there was a gap between that. So here people try to think about the saturation of carriers, whereas MOSFET people try to think about the saturation of currents. So that's why historically, there is a gap, there is a difference in the naming convention of BJTs and MOSFETs when you're thinking about their operating regions. So for BJT, this is called saturation, and this region is called active. For MOSFET, this region is called the linear region or the triode region because you have a linear resistor over here. And this region where your current is saturated, that is called your saturation region or active region. So the saturation region is something that might get confusing to some of you, but keep in mind that they are defined for different terms. For MOSFETs, the saturation is defined as a saturation of current. For BJTs, the saturation is defined as a saturation of carriers. And that's why they sort of signify different regions of operation. Even though the curve looks exactly the same, the phenomena is sort of similar, and also the numbers that we'll be seeing are also very similar. But the naming convention has historically been different. Okay, so that's about your IC versus VC characteristic. Now the next thing is that the small signal model for the BJT. Again, you see that it's similar to what you have learned for MOSFET, but again, it's not exactly the same. For MOSFET, the input impedance is infinite, right? Because your input is applied to the gate in most of the cases, if you're thinking about common source or common drain configurations. So your input is applied at the gate, and at your gate, you have an insulator layer for MOSFETs, right? So no current can go in. You have infinite input impedance, so your input side is open for a MOSFET. For BJT, current can go in because this is a forward bias diode, and current will go in. So that's why you have an input resistance here, which is usually denoted as R pi. And this is sometimes called the pi network model because this looks like an inverted pi. So, and by pi, I mean the mathematical symbol pi, not the food. Okay. So, so this is the mathematical symbol for pi. And if you just invert it, it looks like this model, right? So that's why it's called the pi model for BJTs. At your input side, you have this R pi. And that is because you have a resistance at the input. Your input is not open like MOSFETs, but it's still a current controlled current source. So at the output side, at the collector side, you'll have a current source. And for MOSFETs, this was GM times VGS. In this case, it will be GM times VBE. So again, this is very similar to MOSFETs, right? GM times VBE. But there is one other way that BJTs are analyzed also, that is with this beta factor. And beta is called the current amplification factor. Remember that BJT is a current controlled current source. There is a current, incoming current. For MOSFET, there was no incoming current. You just developed a voltage at the gate, you got some current at the drain. For BJTs, you are sending a current in through the base, and you are getting some current, an amplified version of the current at the collector, right? So beta times IB, that is your collector current. So IC is beta times IB. That is another way to look at this output current. So this output current is GM times VBE, which is similar to MOSFETs, which is equal to beta times IB. Okay. So this is the AC small signal linear equivalent circuit for a MOSFET. So whenever we are doing any small signal analysis, for a BJT, whenever we are doing any small signal analysis for the BJT, we'll be using this model. So the primary difference here is that you have an input resistance, and you may call this current as GM times V in this case it is VBE, or beta times IB, whichever way is easier for you to analyze. All right, so now some more equations related to BJTs. So again, you can draw a BJT circuit and NPN BJT circuit like this, just like we had done for MOSFET, that at the base, you are applying a VBE voltage. So this voltage is VBE. At the collector side, you have a collector current IC. That same current, in case of MOSFET, remember that the drain current was same as source current because there was no other way for the current to flow, right? So that's why whatever current is flowing through the drain, same current flows through the source for a MOSFET. For BJT, that is not true, right? Here the current, here you can have KCL of current. There is a current coming in, there is a current in this direction, and there is a current in this direction. So if you assume that your BJT is a node in your KCL analysis, your IC plus IB will be your IE, right? So that's again one difference between BJTs and MOSFETs. It's not as easy as MOSFETs because in MOSFETs your drain and source currents were similar. Here IC and IE will be very similar, but not exactly same. In fact, IC plus IB will be equal to your IE. So the collector current and base current together for an NPN BJT will give you the emitter current. Okay, and we have already seen this, that your IC, that the collector current is beta times IB. That's the current amplification factor. The BJT is a current controlled current source. The output current over the input current is a ratio of beta, right? Beta is the ratio of your output current to your input current. Now, usually in circuit analysis books, you'll see that this equation will always be provided, that IB equal to IC over beta or IC equal to beta times IB. But they don't really mention that why should there be a beta? Why should there be a current amplification? Right? What is happening inside the MOSFET, or what is happening inside the BJT in this case, which is leading to this current amplification? And why do you actually have a current amplification is because, think about this, that your, let's say I have, And what I'm going to say next will be easier to visualize when you're thinking about a PNP transistor. So let's draw a PNP transistor. So you have a P-type collector. You have N-type base, and you have a P-type emitter, right? So the current is coming in like this. The base current will flow in this direction, because remember that this will be dual of what is happening in the NPN transistor. So the base current is flowing from the base towards left side, and then there is an emitter current that is flowing here, right? So that's what is happening for the PNP transistor. Okay. Now, what's really happening here is that you have a P-type semiconductor here. So there is a flow of holes from this P-type semiconductor. So I'll just draw a semiconductor bar. So you have a P, and then you have a very small n, that is your base. And then again, you have a P-type semiconductor. Okay. So what is happening is that holes are flowing from this P-type semiconductor to the other side of the P-type semiconductor. And in between, they are crossing this N-type base. Okay. So P-type semiconductor has a majority carrier of holes. These holes are flowing from, according to this diagram, from left to right. And in between, they are crossing the N-type base region. Inside the N-type base, the majority carriers are electrons. So of course, when these holes are crossing the N-type base, there would be a recombination of the carriers. So some of the holes that are flowing through the N-type base, they will recombine with the electrons that are already present in the N-type base. Right? P-type semiconductor has an abundance of holes. N-type semiconductor has an abundance of electrons. Again, P-type semiconductor has an abundance of holes. So as these holes are flowing through the base region, because there is an abundance of electrons in the base region, some of those holes will recombine with the additional electrons that are present in the base. Now, you know that you always have to sort of maintain equilibrium. So as some of these electrons are getting recombined with the additional holes, they need to be replenished. And how they are replenished? They are replenished with this extra additional current. Right? Same thing is happening for the NPN case, that you have a current flow from the collector through the emitter. Now, during that current flow, some of the holes, some of the electrons will, so this is NPN, right? So during this current flow, some of the electrons will get recombined with the additional holes in the P-type base. So there would be less number of holes now in the P-type base. So you would like to sort of replenish those holes with a flow of additional current. And that additional extra current is provided by the base current. Now, since the base region is very small and only a few recombinations are happening when the current is flowing, you don't have a lot of recombinations happening. You don't have the requirement of a lot of base current. So that's why your base current is very small. It's only a factor of how much recombination is happening and how large your base region is. So when you study semiconductor physics, this will be much more clearer. But what I'm trying to say here is that this equation is not the cause. It's an effect of the basic semiconductor physics that is happening inside the NPN or PNP transistor, right? So because of the small number of recombinations as compared to the total number of carriers that is flowing from the emitter to the collector, you have a ratio of those two, that how many carriers are flowing from the emitter to the collector versus how many of them are getting recombined in the base region. Because only a very small fraction of those are getting recombined in the base region, the requirement of base current is very small, whereas the current from the emitter to collector is large. And that ratio is your beta ratio. That what's the requirement of your base current and what is the current that is flowing from your collector to emitter, or what is the amount of carriers that are flowing from your emitter to the collector. That gives you the ratio beta. So it's not the equation that governs the physics of the device, it's the physics of the device that governs the equation. Okay. But as circuit design engineers, all we care about is eventually the equation, and this is where most of the circuit books will start. But as you go to a semiconductor physics class, you'll probably understand this better. But I just tried to give an intuitive understanding of what is happening that you have a lot of carriers flowing from your emitter to the collector. Some of those carriers are getting recombined with the other type of carriers inside the base, right? Because the majority carriers in the emitter are different from the majority carriers in the base, because they are different semiconductor, different type semiconductors. So there are some recombinations happening, and to sort of compensate for those recombinations, you always want an equilibrium in your device. To compensate for those recombinations, there is an additional requirement of a base current. And because the amount of recombinations are small, the requirement of the base current is much smaller than the amount of the collector current or the emitter current that you have. And that's why this beta ratio is usually large. It's usually in the range of 100. So you can design your NPN or PNP transistor with a certain amount of beta that you want, but usually the beta is designed to be in the range of 100 or 200 or so. Okay. So that's about beta. What is IE? IE is equal to IB plus IC for this NPN transistor. So that is equal to IB plus beta times IB, because your IC is beta times IB. So this gives you 1 plus beta times IB. So emitter current is 1 plus beta times IB. Collector current is beta times IB. There is another factor that's sometimes described to be a property of the transistor, but that's a derived property. Alpha, that is the ratio of IC over IE. Now you know IC is beta times IB. IE is 1 plus beta times IB. So this is basically a ratio of beta over 1 plus beta. So again, this is a derived parameter, alpha. What you really care about is the beta of the transistor. Okay. And why alpha is important? Because when you think about, just like the MOSFET can be configured into common gate, common source, and common drain, the BJT can be configured as common base, common emitter, or common collector. Right? So when you have a common base configuration, that means your base is a AC ground, right? Your base is a AC ground. You're applying. So what is a common base configuration? Common base meaning the base will be a common terminal. The base will be a in terms of AC, that will be a ground terminal. So that means that will be a virtual ground, right? So where your inputs and outputs will be, your input will be at emitter, your output will be at collector. Just like when you had an NMOS FET and you had a common gate configuration, that you applied your input at the source, you looked at your output at the drain, right? So in this case, what is happening is that you are applying a current at the emitter, you're looking at the current at the collector. So the common base current gain, that is basically your alpha. That is the current ratio of IC over IE, which is almost equal to 1. Beta over 1 plus beta is almost equal to 1. Let's say your beta is 99. So this ratio is 99 over 100, which is almost equal to 1, but not exactly equal to 1. So this is the common base current gain. Whereas beta is basically called the common emitter current gain. So common emitter is analogous to your common source configuration in a MOSFET. Right? Emitter is analogous to source. So common emitter is basically your common source. If you just draw an analogy, it's not exactly the same thing, but you can sort of visualize a lot of things just by if you remember what is common source, and you can visualize what would be common emitter, or how would common emitter look like if you just have that idea of common source in mind. Okay, so that's what we have here. That's the analogy between the MOSFET and the BJT. So the source becomes the emitter, the gate becomes the base, the drain becomes the collector. The equation for ID for the MOSFET is K over 2 V over drive squared times 1 plus lambda VDS, if you are taking channel length modulation into consideration. Similarly here, IC, that's the collector current, that will be equal to IS times e to the power VBE over VT, right? So that's the diode equation that we had written. So what's the diode current? The diode current is the reverse saturation current times e to the power VD over VT. The VD is the VBE, that's this voltage, base to emitter voltage, over VT. That gives you the emitter current, and your collector current is almost similar to the emitter current, right? So you have a ratio of alpha that you can think of, that okay, I can always when you are talking about IC, you can think of it as alpha times IE, but that will also be almost equal to IE for all practical purposes, because your beta is supposed to be high. So again, you see that the equation in this case are not similar, because this was a square law model, whereas this is an exponential model of a diode. So this is one big difference between the MOSFET equation and the BJT equation. But the form or the way it needs to be applied in the circuit is very similar. It's just that the model that we have is square law versus an exponential model. You can also have the effect of instead of VDS, we'll have an effect of VCE. That's the channel length modulation for BJTs. And channel length modulation for BJTs is again called early effect. So it's the same thing. The name is different because different people worked with BJTs and MOSFET 60 years ago. The same people who are working with MOSFETs did not work with BJTs. So the names were different. So this is named after, I think the inventor was J.M. Early. So and this is called an early voltage, VA, which is nothing but your 1 upon lambda for your MOSFET. So see, this is 1 plus lambda VDS for your MOSFET, and this is 1 plus 1 over VA times VCE for the BJT. So early voltage or VA, that is just equal to 1 upon lambda. And graphically speaking, what this is in your output characteristic, lambda was this slope, right? So how much was the increase in current once you entered the active region? After you have entered the active region, you expect the current to be constant, but it is not constant because of this effect. And the slope of that was your, that determined your lambda. What early voltage signifies is that if you just extend this lines, these curves to the left-hand side, they will cross at a certain point. They will cross at a certain point, which is called your early voltage or VA. Okay, so that's why they mean the same thing, that this was 1 plus lambda VDS. This is 1 plus 1 over VA times VCE, but VA is called your early voltage, and which is nothing but your 1 upon lambda for your MOSFET analogy. Okay. Your VGS for the MOSFET was VT plus square root of twice ID over K. This is the equation we have used multiple times in the homeworks and also in the exams. Here, instead of VGS, you have VBE. And VBE is KT over Q, that is VT times natural logarithm of IC over IS. That comes from the diode equation. Now, for active region, you needed to have VDS greater than V overdrive for the MOSFET. Here, there is a concept of VC SAT. Just like there was a concept of VD SAT for MOSFET, here is a concept of VC SAT. But then again, for all practical purposes, this VC SAT value is usually in the range of, let's say, 0.2 volts. So when you're solving BJT problems, this VC SAT will be given. It's sort of like a fixed quantity that we approximate for BJTs, whereas for MOSFETs, this is not a we did not take into consideration as a constant quantity. Rather, we just found out what my VDS is for each scenario or each consideration. Now, this is again the same thing you can do for BJTs, but that just makes the equations more complex. So usually it's assumed to be more simplistic. So you assume a VC to be about 0.2 volts. You can define GM in the same way. So MOSFET GM is del ID over del VGS, and that is square root of twice K ID equal to ID over or twice ID over V of V. In case of BJTs, it's a similar equation, GM equal to del IC over del VB. So you have your equation for IC. You will be differentiating it with respect to VBE. Now remember, this is e to the power VBE form. So when you differentiate it, the e to the power term will remain, right? So it will be IS times e to the power VBE over KT by Q. And then you'll differentiate VBE over KT by Q once more because of the chain rule of differentiations. So that will give you this additional term of KT over Q. So your GM is nothing but IC over VT or IC over KT by Q for a BJT. So you see that the equations are much more simpler for a BJT. So if you know MOSFET, BJTs should look to be much more easier than MOSFETs. Right? So GM is just IC over VT or IC over 25 millivolts. Okay, that is your GM for a BJT. RO is 1 upon lambda ID for your MOSFET. Because lambda is 1 upon VA for your BJT, you just replace it with that. RO is VA over IC for your BJT. So again, you see that there is a lot of analogy between your MOSFET and the BJT. We'll continue from here in the next lecture, and we'll look at the small signal model once again, and we'll look at 1 or 2 problems that you can solve with BJTs. Okay.